Assalamu alaikum everyone. My name is Muhammad Abdullah Afzal, roll number 21TE53. Today we are going to discuss lab 8. The objective of this lab is to implement an analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design. Now moving towards task 1. Define filter. A filter in the context of digital signal processing refers to a system or algorithm that modifies the characteristics of a digital signal. Filters are used to extract, enhance, or suppress specific components of a signal based on their frequency, amplitude, or phase properties. Two types of filters. Low pass filter. Low pass filter allow frequencies below a specified cutoff frequency to pass through, attenuates frequencies above the cutoff frequency, used for removing high frequency noise or extracting low frequency components. B. High pass filter. High pass filter allow frequencies above a specified cutoff frequency to pass through, attenuates frequency below the cutoff frequency, used for removing low frequency noise or extracting high frequency components. C. Band pass filter. Band pass filter passes a specific range of frequencies or bandwidth centered around a central frequency. It attenuates frequencies outside the specified bandwidth. Band pass filter used for isolating specific frequency bands in signal. D. Band stop filter. Band stop filter attenuates a specific range of frequencies while allowing frequencies outside the notch to pass through, used to remove interference or unwanted frequency components. E. All pass filter. All pass filter passes all frequencies with equal gain but introduces a phase shift that varies with frequency, does not alter the amplitude of the input signal but can affect its phase, used for phase correction, creating delay effects or implementing phase equalization. 3. What are the time domain parameters for a filter? Step response. Good step response. A good step response indicates that the filter settles quickly and smoothly to its final steady state value without significant overshoot or oscillations. This ensures that the filter accurately tracks changes in the input signal and responds promptly to signal transmission. A good bad step response. A poor step response may exhibit slow settling time, excessive overshoot, undershoot, or oscillations. This can result in signal distortion, inaccuracies in tracking input changes, and instability in the filter's behavior. B. Overshoot. A good overshoot, a low or negligible overshoot is desirable as it indicates that the filter output closely matches the desired response without significant deviation or transient effects. Bad. Excessive overshoot can lead to signal distortion, ringing, or instability in the filter's output. It may cause unwanted oscillations or introduce artifacts that affect the accuracy and reliability of the filtered signal. See linear phase. A good linear phase. Linear phase is considered beneficial as it ensures that all frequency components of the input signal experience the same phase shift, preserving the signal's waveform and avoiding phase distortion. This is particularly important in applications where phase coherence and signal fidelity are critical. A bad one. Non-linear phase responses such as phase distortion or phase shift that vary with frequency can lead to signal degradation, smearing of transient signals, and altered frequency characteristics. Non-linear phase can introduce distortions that affect the intelligibility or quality of the filtered signal. Part 4. What are the frequency domain parameters for a filter? First, roll-off. A good roll-off refers to the rate at which a filter's frequency response decreases from the pass band to the stop band. A bad roll-off. A poor roll-off implies a gradual or slow decrease in the filter's frequency response from the pass band to the stop band. B. Ripple in pass band. A good ripple in pass band. A good filter has minimal or negligible ripple in the pass band, meaning that the magnitude response remains relatively flat and consistent across the desired frequency range. A bad one. Poor performance is characterized by significant ripple in the pass band, where the magnitude response exhibits variation or fluctuation in amplitude. Poor stop band attenuation. A good one. Good stop band attenuation refers to the filter's ability to effectively suppress frequencies outside the desired pass band, ensuring that unwanted signal, noise, and interference are adequately attenuated or eliminated. A bad one. Poor stop band attenuation indicates insufficient suppression of frequencies in the stop band, allowing unwanted signal, noise, or interference to pass through or leak into the pass band. Part 5. Discuss the role of low pass filter for filtering design. The role of low pass filter in filter designing includes selecting desired frequencies while blocking higher frequencies, preventing aliasing in digital signal processing. This is about task 1. Moving forward towards task 2, the objective of task 2 is plot the signal in time and frequency domain along with its magnitude response. Here we have 4 magnitude response. The first one is x given 1 ratio 40 is equals to 0. As you can see in the source code, firstly we can define the signal x, then plot the signal in the time domain, then compute the Fourier transform of the signal and compute the magnitude response, then plot the magnitude response in the frequency domain and plot the signal in the frequency domain. Here you can see the output in the output picture. Second magnitude response is x of 41 ratio 120 is equals to 1. As you see in the source code, firstly we define the signal, then plot the signal in the time domain, compute the Fourier transform of the signal, compute the magnitude response, plot the magnitude response in the frequency domain, plot the signal in the frequency domain. Now moving forward toward third magnitude response, that is x of 121 ratio 161 is equal to 0. As you can see in the source code, now we apply above mentioned step and you can see the output in the output picture. Moving forward towards fourth magnitude response, x of 121 161 x of noise is equal to x plus 0.5 into random size of x. As you can see in the source code, we can perform all the same step as discussed above. You can see the output in the output image. Now part B, apply 3 tab symmetrical around moving average filter on signal X noise and observe the time and frequency domain parameters. You can see in the source code image, we perform all the above mentioned step. You can see the output in the output picture. Part C, apply 11 tab symmetrical around moving average filter on signal X noise and observe the time and frequency domain parameters. You can see the source code and just below the source code you can see the output of 11 tab symmetrical around moving average filter on signal X noise. Now for 25 tab symmetrical around moving average filter on signal, you can see the source code and just below the source code you can see the output of this lab. Now task 3. Task 3 is about repeat example 7.2 with 7 tab, 17 tab, 17 tab and 51 tab and 101 tab. Observe the frequency domain parameters. You can see for 17 tab coefficients. As you can see in the source code, all the parameters are defined. This is the output image of magnitude frequency response. Now for 51 tab coefficients, this is the source code for 51 tab coefficients and this is the output for 51 tab coefficients, and we have graph magnitude frequency response. Now for 51 tab coefficients, you can see the source code and this is the output image of magnitude frequency response. Now part B of task 3. Apply the filters made in part A to the signal X signal. Observe the changes for signal X in time and frequency domain while varying the number of coefficients of the filter. As you can see in the source code, we define all the parameters and this is the output image of the part B. Now task 4, part A. Repeat 7.3 with 7 tap and 17 tap. Firstly, we have source code and we define all the parameters, and at the end we plot the signal. This is the output image of frequency response of 17 tap finite impulse response band pass filter. Now part B. Apply the filter made in part A to the signal X signal. Observe the changes for signal X in time and frequency domain while varying the number of coefficients of the filters. As you can see in the source code, we can define all the parameters, and at the end we plot the signal. This is the output image of firstly we have original signal in time domain, original signal in frequency domain, and filtered signal with a tap FIR band pass filter in time domain, and at the last filtered signal with 5 tap FIR response filter frequency in frequency domain. That's all about today's lab. Allah Hafiz. Thank you so much.